Good morning. Welcome to the Founders Day lecture at the Raman Research Institute. As you know, the institute was set up in 1948 by Professor C.V. Raman, and a year back we just completed the Platinum Jubilee celebrations for the 75 years of very high scientific heritage that we are carrying forward, and I'm very proud that the current faculty are keeping up with the highest levels of research that is being recognized globally. So last two Founders Days were 7th November, which is the birth anniversary of Professor C.V. Raman, as a Founders Day and with a Founders Day lecture by an eminent personality. So I'm delighted that Shri Kiran Kumar accepted our invitation to deliver the Founders Day lecture this year. So he doesn't need much of an introduction to the audience here, but nevertheless, he has been the former chairman of ISRO and during 2015 to 2018. He currently also holds extremely high responsible positions. He is the chair of the Management Council and member of the Space Commission Management Council of Physics Research Laboratory and member of the Space Commission. He's also the chairman of the EPIC Science Board, and also should be mentioned, but everyone knows he is also the chairman of our governing council at this time, and we are really helped by his guidance for the last 2 years. So Shri Kiran Kumar was born in 1952 in Hassan, Karnataka, so he is very much a man of the soil here, and he has really made Karnataka proud, and he has been very, very influential in moving the space program forward. His forte has been to steer the implementation of application-oriented Indian space program, and which facilitated rapid development in various aspects like Earth observation, communication, navigation, meteorology, and space sciences. In particular, he has been the person behind the Chandrayaan mission, and this, as many of you know, has been a long program with multiple Chandrayaans, which has also, resulted in a lot of acclaim for the space capability of India. And also, of course, the Mars orbiter and other missions that are coming up now are also being done under his guidance. Of course, someone like him would have been recognized in multiple ways, and so I won't really go through the entire list. I should mention he was conferred the Padma Shri by the President of India in 2014, and he's got the Rajyotsav Award in 2015, and many other lifetime achievement awards, and of course he's been the President of Aeronautical Society of India, Fellow of the Indian National Academy of Engineering, National Academy of Sciences, and societies related to remote sensing, and similar many such societies related to these areas. So I don't want to really come in the way of the talk that is promising to be extremely interesting. Everyone is proud of Indians' lunar exploration and what we have achieved, and RRI is very happy to bring the story to you from so-called the horse's mouth, as you would say it. So, Shri Kiran Kumar, please.
Thank you, Tarun, for that generous introduction. At the outset, I am extremely privileged to be present here as part of the Founders Day, where a great son of the soil who demonstrated immense capabilities and showed to the world that even with very little resources, you can achieve great things. And in fact, we need to remember him for that. And this institute itself is actually the handiwork of that great individual. And on this day, remembering him is nothing but reminding ourselves of the past and what we need to do in the future. So thank you for this opportunity to be part of this program. In fact, I remember as I was studying in National College in late 60s, in the same hall, I had the privilege of listening to Sir C.V. Raman. And on that day, he spoke about percussion instruments and mathematics of that. In fact, that was the first and probably the only time I had an opportunity to physically see him. Beyond that, what we have been reading and what we have heard is legendary. So what I intend to do today is just take you through an activity which also in many ways is a result of what Sir C.V. Raman contributed, I should say. Because one of the key students of his, Professor Vikram Sarabhai, is the person who was responsible for our India's activities in space. So if you see, so actually even Vikram Sarabhai, when he came back from Cambridge, he was studying under Sir C.V. Raman. And then it is his ability to look beyond what is happening today, and then how a technology of being able to go beyond planet Earth can be made to benefit the country. You can visualize in 1957 when the first object went up into space, India was a fledgling democracy, just 10 years into independence, struggling to provide food, shelter, education to its citizens. At that time, if somebody were to look at how the activity of going to space can make a difference, it's a great visionary mind. And it is such minds which have been actually inspired by the founder of this institution. So in fact, in the initial days, the India started the activity of doing space for necessarily providing weather monitoring, communication, broadcasting. A whole lot of things happened right from 63 onwards. And then Earth observation, SATCOM application, navigation, disaster monitoring, and strategic application as the country kept improving its own ability to provide solutions to its citizens. It also became a place where you need to compete with your surroundings and make sure that you are protected. So strategic activities also start becoming an important aspect of space program. And while all this was going on, the India had actually shown that you could build your own launch vehicles which can take you to low Earth orbit, 500 to 900 kilometers, and geostationary orbits from where the platform can look at Earth almost, you can say, 24/7. That is 36,000 kilometers. And then as the technological capability of the organization kept improving, the task is you need to make sure that you are provided more and more challenging tasks. If those challenging tasks are handled, then your ability to solve problems also improves. So it was looking at how we can put our instruments and our ability to go beyond geostationary orbits. So Moon, which is almost 3,85,000 kilometers, and then Mars also became targets of the activity. And one of the key things was, as India demonstrated right from its inception, whatever technology is accessible to it, make use of it and try to achieve the goals you want. So the launch vehicle, what we had developed till that time, was capable of only putting few tons to geostationary orbit. And with such a launch vehicle, if you were to go to Moon, then enough capacity is not there, enough thrust is not there. So you have to come up with a method of achieving the requirement in a different mode. And in fact, India was, you can say, the first country which adopted this method of using every time the satellite comes to the perigee of an elliptical orbit, you use that opportunity to marginally increase its velocity by firing your engines and then push the satellite to a farther and farther distance. And Chandrayaan-1 itself was conceived with this mode of operation. And when we were able to successfully demonstrate that we could reach moon and get into a lunar orbit, it was a very significant development at that point of time. And also this particular mission was actually an excellent example of international cooperation, because more than 5 countries' instruments were carried in our launch satellite, and the satellite provided a unique opportunity simply because, though by that time when we went in 2008 October, man had landed on moon long back and a large number of probes had touched the surface of the moon, this particular mission gets the credit for discovering the presence of water molecules and the process of water molecule formation, because the satellite carried instruments which were actually otherwise not getting opportunity to go to moon, and a couple of them were of course from US, both APL and JPL. And this particular mission was actually a significant demonstration of how with limited resources you could do many things. So this is what I was trying to explain. The way we adopted the process was put the satellite into a elliptical orbit from the launch vehicle what we have, and every time the satellite comes to the perigee point with the engines that are present on the satellite, and using them you progressively improve your orbit altitude, and then do exactly reverse, because you're all very familiar. If you want to put any object into a celestially another planetary platform, what you need is, depending on at what height you are, you need to provide a specific velocity and a specific direction. If your velocity matches that, you will get into a circular orbit. If your velocity is less than that, you will get into the point of injection becomes apogee or apolunar, and then the other point becomes peri, or if the velocity is inadequate, it will go and hit the planetary surface. And if you are able to put more velocity, it will go to a progressively increasing orbit. So when we are inserting into moon, the requirement is you do not have enough velocity to be given. So you will be in an elliptical orbit to start with. Then progressively you keep on providing velocity reduction to the satellite so that you get into a circular orbit. So you reach, this actually shows in terms of animation, sorry. Can we play this on the video? Yeah, of course, this is just an illustration of the same thing. Every time the satellite comes to the perigee, this keeps changing. So this was the technique that was adopted. And in fact, we were the first to do this in that context. And then as you come very close to the moon, then you do the reverse operation. And then you start with a highly elliptical orbit, and then progressively you reduce it and reach the circular orbit that is intended. And what was achieved was 100 kilometer by 100 kilometer circular orbit in the end for this. So the mission itself, like I pointed out, it carried 6 payloads of other countries. And we also carried an instrument called a Moon Impact Probe. We will see some results of that subsequently. The instruments contained from our own terrain mapping camera to provide 3-dimensional images of the moon surface, a hyperspectral imager, a lunar laser ranging instrument, high energy X-ray spectrometer, moon impact probe, and then Chandrayaan-1 imaging X-ray spectrometer, then smart near-infrared spectrometer, and some of these were from our other countries. So of course, in terms of the findings, it actually demonstrated the presence of hydroxyl and water molecules, and then the presence of large expanses of crystalline feldspar on the lunar surface. which validates the lunar magma ocean hypothesis. And then the reflection of solar wind protons as neutral hydrogen from lunar surface. Like this, there were and also a couple of rails connected subsurfacially by an undamaged lava tube, which is also a possible place where humans can or get themselves protected from radiation. So these are some of the images results from that. And you can see here, this is a rail, what is a this portion of the segment is actually not collapsed, and rest of it is a collapsed segment. So this can provide a natural tunnel type of situation. So when later humans want to get in, it could be a safe place for future human habitats. And you can also see that kind of images that could be generated, three-dimensional images of the surface. And then many papers got published from this. And protons reflected from magnetic anomaly regions were also some of the findings from this. Over the whole far side of the hemisphere, the total deflection efficiency is about 1%, and over the anomaly regions alone, it's 10% and more, and could go up to even 50%. These are some of the work done by PRL scientists, and discovery of a new population of suprathermal protons around moon. These were, again, some of the observations from that. And there were also experiments conducted by observing the S-band radio signals coming from the transmitters on the orbiter, and by making measurements on ground using our large antenna, the ionosphere of the moon also studies were carried out. This was another very interesting thing that was done, a moon impact probe, which in the very first mission also, this impact probe would come out of the orbiter and then go and touch down on the surface of the moon in an uncontrolled manner. So this was the first attempt by us to send an object onto the surface of the moon. And this was over 29 kg instrument, and from 100 kilometer orbit, it went and finally touched a place which is later named as Jawahar Sthal. That means the place where it impacted near Shackleton crater. It is called as Jawahar Sthal. And it demonstrated quite a few technologies. And in fact, this idea of putting a moon impact probe on our first mission was also an inspiration by Dr. Abdul Kalam. And then this was actually worked up and then incorporated at the last minute entry. And it did provide very interesting results. One of the things was, of course, it carried a chase, that's the altitudinal composition analyzer mass spectrometer. And in fact, this was the first instrument which actually picked up information about the presence of water molecules very close to the surface of the moon. But in any scientific finding, you know, before you can prove what you have observed is valid or not, it requires a large amount of collaborative and corroborative evidences to be picked up. So by the time that was done, because this was the first instrument flown, and by the time all the calibration issues were resolved, the M-Cubed from the US and also the MINISAR had done their homework and then showed that water molecules and OH molecules presence had been already discovered there. But then this is the first instrument which actually did in situ observation and got validated later. Another thing that we carried on that was a camera, and this camera took pictures of the moon as it descended from the moon impact probe, and it covered an illumination range, and then it took pictures between 13 degree, minus 13 degree to minus 89 degree latitude, and the kind of pictures it could take as it is. The moon impact probe itself was stabilized by rotation. You will see that the images are actually rotating, and they become higher and higher resolution as they move back. Just to, sorry. Okay, you can see now. So these were way back in 2009 when it happened. Then after completing the Chandrayaan-1 mission, the next Chandrayaan-2 mission that was planned was for actually an orbiter and a lander. So this happened in 2019. And here again, basic elements were very similar. We were attempting to put the satellite into a highly elliptical orbit and progressively reach moon. And then after reaching the moon, you had components like an orbiter and a lander and a rover. So all this was planned. And then, of course, on in this particular attempt, while the orbiter worked very well and continues to provide significantly important data, we just fell short of touching down in this particular mission. So what it carried was again a terrain mapping camera and a class instrument, an infrared spectrometer, and also synthetic aperture radar. In fact, what was done in Chandrayaan-2, in Chandrayaan-1, we had carried instruments built by JPL and APL, which were the synthetic aperture radar and also the hyperspectral imager. And in the infrared region, here we built those instruments ourselves in India, and then we had, instead of single frequency SAR, we had built a dual frequency SAR, and that was what was carried on this. And then some of the work that had happened in Chandrayaan-1 had to be pushed further, water on the moon, make observations more systematically, cover the entire moon surface, and then study lunar topography and also the composition was the attempt that was being done. So one of the things this carried was also a very high resolution imaging camera. In fact, this happens to be the highest resolution imaging camera orbiting moon. And in fact, it is the result from this which enabled us in Chandrayaan-3 to achieve the success what we were able to realize. And it produces 25 centimeter resolution images. And then these are some of the images taken from that. You can see even very small boulders or small rocks, etc., can be seen very clearly. And in fact, in Chandrayaan-2, we did not have the privilege of such images for planning our touchdown. I'll come to that point a little later. So these are some of the images taken from that particular very high resolution camera system. And then we also had, of course, a terrain mapping camera. Terrain mapping camera is nothing but a stereo imaging system looking at the object in 3 views, and by picking up that data and during parallax and mathematical formulations, you can generate 3-dimensional images of the surface. That's what was done. So this is a continuation from Chandrayaan-1. And you can see some of the types of craters, and that could be generated using the data from this. This is again a Sarabhai crater. One of the craters on moon is named after Vikram Sarabhai, and this is an image of that. And then probably you are just mentioning, this is probably the image that was covered in the first slide. And you can also do a lot of activities by determining the reflection characteristics, and by studying that and then using models, you can determine the impact direction and impact ejecta, actually in what portions it falls. So this is an instrument, dual frequency synthetic aperture radar. So what I was mentioning is, in Chandrayaan-1, a mini SAR was an instrument built by APL, American Institute, and when in Chandrayaan-2, we built this dual frequency SAR, both L-band and S-band, and this was the one which was flown. And in fact, it is this instrument which has been responsible for making many significant observations on the lunar surface, and also coming to conclusions on unambiguous detection of water and water molecules on that. In fact, it's also a technologically a very compact instrument, just about 20 kilograms and 115 watts of power it takes, and operates in L and S band. And the kind of data that has been generated using this is the entire polar surfaces, both south and north poles data have been collected. And it also has multipolarization. So multipolarization enables you to evaluate the very many different parameters from the images. And a lot of work has gone on in identifying the various aspects of the lunar surface, including dielectric constant and many other parameters. So this is actually an example of radar, is its ability to detect hidden melt flows around the old craters, and also it shows an impact flow that appears to be covered by a regolith layer. So such activities have been done using the data. and detection of potential water ice bearing regions on the North Pole. So whether it's porous ice or pure ice or dirty ice, such activities have been done by processing the images collected from this. This shows you the kind of mosaics that have been generated for the North Pole and South Pole of this. And it also has many impact features, and subsurface feature information extraction all becomes a possibility using this SAR data. And of course, this again another example of fully polarimetric SAR. One other thing we need to appreciate is in any other region, permanently shadowed regions which are there, the best way of interrogating and doing is if you are able to carry an active sensor. So radar provides you that, and also of course if you can carry LIDAR, then you can bounce the LIDAR off and do. But the microwave provides you some penetration. So using that, you can see even in the crater depths on permanently shadowed regions, the activities are done. Subsurface feature extraction. So similarly, the instrument that was done was an infrared imaging spectrometer. Infrared imaging spectrometer operates up to 5 micron in comparison with what we carried in Chandrayaan-1. The JPL instrument was able to go only up to 2.9 micron or 3 micron, whereas this instrument was built to cover up to 5 micron. And as a result of that, significant contribution to many studies, both with respect to mineral identification, mineralogy, this has enabled. And then it is able to look at locations of regions of interest corresponding to the, of course, there is some work that is going on for the LUPEX mission, ISRO JAXA mission, and some of the work which is identifying the possible landing areas and then identifying what kind of features are there is all done using this data. And here again, identifying hydration associated with the Shackleton crater using Chandrayaan-2 IIRS data sets. And many of these have got published in Lunar Planetary Science conferences, etc. And then again, in the volcanic areas, in the Compton-Belkovich volcanic complex, some of the work that is done is showcased in this. And here again, the estimation of the complex region using the Chandrayaan-2 IIRS observation, it shows what has been possible of how much of water percentage in ppm, starting from 100 ppm to up to 1000 ppm. It's possible to make estimations, and these estimations have been carried out using IIRS data. And also fractional abundance of different materials are done, whether it's low calcium pyroxene or high calcium or regolith within the crater. So many such things have been done using this Chandrayaan-2 IIRS imager. And it's also shown in comparison with Chandrayaan-3, the hyperspectral imager from JPL. And another instrument that was there is actually able to measure the argon distribution on the surface of the moon. And then another very interesting instrument is a solar X-ray monitor. Though it's carried on Chandrayaan-2, it has actually currently happens to be the most sensitive instrument observing solar X-ray spectrum. And then it has made huge impact internationally also for solar physics related activities. And this is an instrument developed at PRL and has been flown. And you can see the long-term light curve, how it is changing from 20 onwards till 24 on a 4-year period. Then many of the results are showcased here. It's more than 20 publications have been done after launch. And then coronal heating. One of the problems of coronal heating is identifying the micro nano flares and their contribution. So in fact, this is, since it was the most sensitive instrument, it has been able to provide significant inputs for such activities. And today there are a large number of users who are routinely downloading this data from the ISSDC data center. And another thing that was also done is using both class and XSM, the actually complete mapping of magnesium and also silicon has been done using the data collected from that. So this shows the identification of different types of molecules and material present, which could be done using class. Then, of course, here, few things probably we need to remember is, in Chandrayaan-2, one of the objective was to take the lander and touch down on the surface of the moon. And here, what you need to appreciate is, if you want to go and land on the surface of the moon, the task cut out for you is the object which is orbiting the moon, you have to make sure that the velocity of that object is reduced such an extent that horizontal velocity becomes zero. And when horizontal velocity is zero, the moon's gravity pulls the object towards it. And if you want to prevent it from getting accelerated and hitting the surface, you have to provide a counter force, and that is what is to be done by an engine. So till Chandrayaan-2 mission, we had been developing engines in our launch vehicles and satellite operations, such that once the engine starts firing, the amount of thrust it generates is fixed. It's not a variable component, and only the mass or the fuel keeps getting depleted. Whereas in this particular mission, you required an engine which had to be throttled, because unless you reduce the means the thrust that you are giving to the object, as you keep coming down with a fixed thrust, because mass is depleting, acceleration will increase and it will go and hit the surface faster. So you need to make sure that as you keep expending your fuel, you have to reduce the thrust. So we had to build the engines which were requiring to operate in a throttleable manner. And this was the first attempt. And we had built new engines, and then, like in any new engine development also, you go through ground characterization. And after that, based on your ground characterization, you plan the activity and perform. So 4 of the engines had to operate in synchronization. And you can imagine, if there are 4 engines, if they are not operating in synchronization, you can have topsy-turvy, and plus the limits of its operation gets into your design feature of what margin is available in dealing with whatever non-nominal conditions you encounter. So in Chandrayaan-2, our problem was, here if you see in this particular image, whatever this distance that is shown here, you start from a height of about 30 kilometers and you come down to the surface of the moon after covering nearly about 680 to 700 kilometer traverse. So over that time, what is the place where you will land, you should know very clearly, because the object which touches down has the 4 legs. And if one of the legs is sitting on a crater or a boulder, then it will topple. So you have to make sure that it reaches a place which is relatively flat. And then you should make sure that you are at the right location. And for achieving that, from the starting point with a velocity of 1.6 kilometer per second horizontal velocity, and then making sure that during this entire period, you control the object. You just need to know its velocity, you need to know its direction, and you need to make sure all your control algorithms are proper. So in Chandrayaan-2, of course, we were able to do almost everything except the last minute activity, where the engine dispersions and consequent algorithmic limitations determined the vehicle, instead of touching down with a very low velocity, it touched down almost with 30 to 40 meters per second. It's almost like 100 kilometer per hour type of the velocities that was there, 200 kilometer per hour velocity. So what we did subsequent to that was, of course, we determined what were the limitations. That means identifying what were the problem areas, and based on that, Chandrayaan-2, we went ahead. And then the efforts that were done in Chandrayaan-3 showed that all the attempts to succeed was actually demonstrated. So here, of course, what was done is the design of the Chandrayaan-3 itself was again very much similar to Chandrayaan-2, but then the lessons learned from that, inadequate resources available in terms of fuel, we made sure that we had more fuel available for the final touchdown. Then you also built in mechanism into this mission where in orbit you would be able to test the performance of the engines, characterize them, and if you find any differences, modify your algorithm so that you can correct for the operations. So that feature also was built into the thing. And so in our on-orbit testing and evaluation was the new aspect that was included. And then another major thing, of course, was preparing the entire region of the coverage. I'll just touch upon that in a subsequent slide. Okay, so our journey was very much similar to the previous cases, going through elliptical orbits and reaching. And then probably here I'll explain on that. So you can see here almost about 745 kilometer range on the moon surface. This entire range image was taken using our OHRC data in Chandrayaan-2. So we knew exactly what is the path and then how things are varying. And in Chandrayaan-2, our target was only a 500 meter by 500 meter margin. Whereas in Chandrayaan-3, we had identified a location which could be 4 kilometers by 2 kilometer area. Within that area, any 100 meter, you are capable of touching down. That means no matter where you are in that 2 kilometer by 4 kilometer area, you can actually safely touch down. That means your error margin with respect to the target is significantly increased compared to Chandrayaan-2. That was possible because we had our own source of very high resolution data, which we were collecting from Chandrayaan-2's OHRC. Otherwise, in Chandrayaan-2, we had to depend on data collected from other sources. And obviously, you will not get everything that you want. You will get some limited information. That was one of the things. Second thing was, of course, between the starting point at 31 kilometer height to reach this, the entire planning that was done, building the instrument, navigation instruments and the algorithms that were there, they were all verified and then made sure that you could achieve. So starting point also, if you see, we were able to determine if you want to achieve, you want to go from place A to place B, and you are depending on completely inertial sensing systems, you should be sure of your starting point and you should be sure of your ending point. End point, I already pointed out, we built larger error margins. Now, starting point also is, you need to know the position of the satellite at the time you initiate the engine firing. That means that at that particular instant, where you are in space, in relation to moon becomes important. That means your ability to determine the orbit is also very critical. Now you are talking of here few tens of meters, not kilometers in error, because finally, if you make a few meters error, then the object where it's going to touch down can become problematic. So here again, our experience of keeping the tracking and orbit prediction for Chandrayaan-2 came in handy, because for almost 4 years, we had been perfecting this task. And when we started the operation for Chandrayaan-3 descent, we knew exactly where the satellite was at the instant of the initiating the power descent. And here again, you have to imagine that all this data is fed into the controls computer systems of the satellite, and then it's all programmed and used with the initiation of a particular command on time instant, it starts the activity. So that absolute time verification also becomes important. And then because you are moving at 1.6 kilometer per second, 100 millisecond itself is 168 meters, so it can produce large errors. So that was achieved. Then other thing was, you can see here, from starting from here, you go through various phases, and you come to this point, you are exactly above the place where you want to land. And then you are built a mechanism of hovering there and take an image and compare that image with the reference image what you have got. And by making this image to image comparison, you can determine whether you are exactly over that place or you are displaced. So you could achieve the requisite performance by coming. And in fact, actually, we were within 100 meters of our originally planned location. And then everything went on very smoothly. And you saw the result of that. So what was the changes between Chandrayaan-2 to Chandrayaan-3 is, we had made sure that the resources which we carried in terms of fuel, in terms of the ability to monitor and evaluate the performance of these engines. They were all built into the mission, and then made sure that everything is verified in orbit, and that's what finally led to successful landing. And then, of course, I'm sure you would all have seen the results of the actual landing and rover coming out and doing many activities. I'll just actually show you a video of what all goes behind the activity before such a thing is realized. This will give you a glimpse of the kind of work that had gone on at your satellite center in preparing the satellite.
The Chandrayaan-3 spacecraft consists of a propulsion module and a lander module with a rover accommodated inside the lander. The propulsion module and the lander module are stacked together to form the integrated module. 6 modules were realized during Chandrayaan-3 project life cycle, out of which 3 were flight modules and 3 were special test modules, namely the integrated cold test, integrated hot test, and lander leg drop test modules.
The main function of propulsion module is to carry the lander module from launch vehicle injection till lander separation. The propulsion module was made ready for further integration with lander module.
A 6-wheeled rover is accommodated inside the lander, which would be deployed onto the lunar surface post-landing. Rover solar panel deployment and illumination test, rover standalone EMI/MC test, vibration test, thermovacuum test, and mass property measurements were carried out. All tests associated to rover were successfully completed, and the rover was made ready for further integration onto lander. After integration, detailed IST, sensor level alignment, and EMI/EMC tests were also carried out before shipment to ASTE Bangalore. A new facility was realized at SDSC Shar for conducting the IHT, craters and boulders simulating hazards during landing. A total of 20 tests were successfully conducted, which include 6 dry runs, 8 static tests, and 6 dynamic closed-loop tests. The lander leg drop tests were carried out to evaluate the energy absorption capability, strength and stability aspects of lander legs during touchdown. A new facility was realized at iSite with a testbed with flat and 12-degree inclined drop surface. Detailed tests were carried out at damper level, single leg level, simulator level, and QM structure level for various touchdown velocities on flat and slope surface and on lunar soil simulant and hard surface. A total of 15 drop tests at simulator level and 2 drop tests at QM structure level were conducted successfully. The objective of lander is to demonstrate safe and soft landing on lunar surface. Major elements of lander include sensors, after the completion of thermal elements in the rover compartment, the rover was assembled onto the ramp using 3 hold-downs. Detailed assembled mode IST was carried out, followed by mass property measurement, thermo-vacuum test, solar panel assembly and illumination tests, EMI-EMC test at CATF eyesight. This was followed by pre-dynamic deployment of secondary rover ramp, primary ramp and rover rollout from lander and payload deployments such as ILSA and Ramba, chased, and the lander was made ready for further activities. Once the lander module was ready, it was stacked over the propulsion module to form the integrated module. EMI-EMC, vibration tests, acoustic tests were carried out. Final finishing activities such as MLI sealing, Chandrayaan-3 spacecraft was made ready for shipment to spaceport at SDSC Shar.
Yeah, so you can see that behind the scene a lot of activity goes on to make sure that every aspect is verified. And then if you see Chandrayaan-3 mission itself, to soft land on the surface of the moon was successfully done. And then there was something more that was done beyond what was originally planned also. And of course, the alpha particle X-ray spectrometer did provide significant inputs based on the rover activities. And then there was also a ILSA instrument which was there, and it measured for the first time in the south polar region of the moon. And then some other observations include first ever detection of sulfur, and then constituents like carbon, and then temperature measurement using the chest, and then ground vibration, saw that. So of course, LIBS instrument, you can see that this was carried, and this is one of the instruments developed at LEOS, and it made measurements using its 9 days of operation. It collected a large number of observations, and then using that, the various molecules that have been detected using that is shown in this particular slide, which shows sulfur, magnesium, aluminum, silicon, and many. In fact, it also indicated the presence of minerals like limonite, anorthosite, etc. And then this was another instrument which actually penetrated up to a depth of about 100 millimeters and then measured the temperature gradient on the surface. And in fact, originally the instrument, the whole activity was planned with one position of the lander, but then later we also did another hop experiment where the lander went up and came down again. This shows some of the results with time, the measurements and how it changed with that. And then the pre-landing site was again using characterized, and based on the data collected, some studies have been done at PRL for demonstrating some of the capabilities. This is the ILSA output on a particular location. And then there was also an instrument which was actually measuring the plasma on the near the surface of the moon. And then this instrument was called Ramba. And then later, the lander position was picked up both by Chandrayaan-2 imager and the radar instruments. And this is another test that was done. Since the entire activity of touchdown could be carried out with minimum expenditure of the fuel, we still had huge amount of fuel available. So an experiment was conducted where the lander was made to go up and then come back. So this was an experiment which was not originally planned, but since we had the fuel and we had the ability to do that, this was attempted, and it was shown that you could do actually modifications to your planning based on the subsequent information set that you get. And this was a technology demonstration in a way for a future takeoff from a landed object. Then another thing that was also done is, instead of leaving the propulsion module which carried the lander and rover, the propulsion module was brought back from lunar surface towards Earth. And originally the plan was to come back into a fully the Earth orbit and then even enter the atmosphere. But of course, the amount of fuel that was remaining did not permit us to do that. But we demonstrated that you could come out of the lunar orbit and you are no longer a debris in lunar orbit, so you came back to that. That was also demonstrated using this. So if you see in the end, the extended mission accomplishments were also done, hopping experiments of the lander and return of the propulsion module from the Earth's orbit. These things are also carried out using this mission. Then if you look at now how things are going to change and make, already you are familiar, the government has approved Chandrayaan-4 mission, and also it has approved the mission for landing on moon by 2040. So if you look at that, what kind of opportunities will be there and what are the activities that are likely to go on. So since you're going to land on moon by 2040, that in itself is also not going to be an end. It's going to be a beginning of a huge amount of activity that will happen for future. So looking at moon as a base for future missions to Mars and other destinations, then human habitation beyond Earth, then many scientific activities using moon as an observatory, then in situ resource utilization on the moon, and also trying to do both manufacturing activity and also extracting the economically beneficial material from that surface. And then as a platform for international partnership is all part of the future activities that are planned. And this year, it's also, we are going to have an activity where in space, you will have two objects docking and undocking, because the next mission to moon is a sample return mission. So sample return mission means you'll touch down on the surface, pick up the material and bring it back to Earth. So for that, you need to have a whole lot of demonstration. So what is planned is a SpaceX experiment this year, and then elliptical orbit docking experiment. Then Gaganyaan mission, of course, is the humans going into the orbit. And then Chandrayaan-4 lunar sample return mission. This has also been approved now by the government. LUPEX work with Japanese government for a possible mission. And then between 27 to 34, you will have technology demonstration mission for lunar crewed mission. Then by 35, are expecting to have Bharti Antariksh Space Station. That means human-rated launch vehicle and crewed lunar orbital mission for that preparatory activities. Then 37 and 38, unmanned human lander and return mission. And then 2040 is the target for landing on the moon. And then in the intervening period, you will have a whole lot of activities going on, which shows that long-term mission with, one of the things probably you would remember is our ability to use the rover for a long period on the lunar surface was limited by the power source we had. So if you are able to carry radiation-based power sources, then you can operate the instruments for much longer period. And for future, obviously, you'll be looking at methods of carrying your own sources of power. So RTG-related experiments will be done. Sorry. And then 35, the Antariksh station I talked about. And then actually, you will have a Bhartiya Chandrama Antariksh station, then compatible docking and cargo mission, and 45 and beyond, mission for sustainable human presence and around the moon. So these are, of course, is all in the planning phase. And then as the things progress, you will see that India moving ahead in this direction of using moon as one of the intermediate stops for various celestial activities. So I thought that in a nutshell is what I wanted to tell you about. I'll end my talk with just a couple of interesting quotes from Professor Sarabhai. which I think is very relevant even today. See, one of the things he said is the important ingredient for satisfactorily meeting the challenge of the changing environment is not experience, but an ability to learn. Many times it appears very counterintuitive. In fact, when Dr. Sarabhai was given the task of running Ahmedabad Textile Industrial Research Institute, he put an advertisement in paper which said, those with experience need not apply. So actually his point was, see, if you want to solve a new problem, then you need people who can think beyond their current thought process, who are ready to look at the problem from all perspectives. And you need people with experience if you want to maintain certain things, run, and then ensure that what is already established is going to continue. But if you want to make new things to happen, then the experience many times may become a liability rather than an advantage. Then experience is less relevant than knowledge, and the ability to learn and innovate. Today, we are all seeing this happening in all spheres. Things are changing at such rapid pace. So what we have learned yesterday may become a liability to us if we are not ready to learn new things. Then another very interesting statement that he had made was, here we can see that not only Sarabhai is there, his guru is also there in this slide. Technology is not an objective to be aimed at, but a tool to be used for the benefit of common man. And in fact, if you see what Sarabhai attempted and what ISRO and Department of Space attempted, is bring in this technology of being able to go beyond planet Earth, make use of it and provide solutions to the people on Earth, and using it as a tool and not as an end in itself. So I'll end my talk here, and I'll be more than happy to answer any of the questions to the best of my ability. Thank you very much.
Thank you for that great talk. Do we have questions from the audience?
So thank you for the talk. It was really nice to get a detailed overview. The question is, do we know the extent of radiation damage that happens in the lunar flights, and what does it mean for human travel to the moon and back?
Okay, if you're asking about the impact on the humans, still very little effort has been done in whatever activities we have carried out so far. The only information we have is on the electronic gadgets, memories, what kind of things we have seen. But otherwise, to come to a conclusion on what is going to be the impact of these radiation in this environment, we still will have to depend on what others have done so far. From our own missions, we do not have much additions to that knowledge.
Thank you. Any more questions? Yeah.
Thank you for this nice talk. And I have a question related to moon surface usage and its international governing. Is there anything that exists currently that what can be done and what part of the moon what can be done, particularly radio quietness at some parts?
Yeah, of course, this is now, as you can see, before Chandrayaan-1, in many ways, the interest to go to moon itself had come down. But after Chandrayaan-1, with the determination that water is present, a lot of interest got generated. And you have seen in the last few decades, and in fact, even during the course of our own journey to moon, you saw very close to our mission, there was a Russian mission followed by Japanese and again. So there is a lot of interest to go to moon, and then you also are seeing not only nation states, but also private entities are doing this. So in this context, the question you pose becomes important. But then the current mechanisms that are there to deal with this, UN and also International Astronautical Congress, where a lot of discussions happens on what should be the kind of activity that should be allowed and whether you should have, what kind of problems can come, both in terms of radio noise. Currently, any instrument that is carried, any orbiter that is carried, what frequency you use, what bandwidth you use, they are all discussed, and then some agreements are arrived at based on which you can do. Currently, one of the things that's also going on is providing navigation capability on the moon surface, so that on the moon, like what we have GPS, kind of lunar navigation system. There again, what should be done? Then what amount of sources can be carried which can become problematic for other observation? These are all questions, but right now there are no, you can say, satisfactory answers or satisfactory regulation mechanisms which have been arrived at. But these are discussions which are going on at forums like UN COPUS and IAC, where interested parties are trying to bring this up for discussion, and dialogues are going on. Otherwise, you are also probably very familiar, there were some companies which were selling land on moon for $25. So, you know, it's a purely the human ingenuity of what you can do. And in the end, of course, it's also the might is right what will prevail. If you have the capability and the competence to do what you want, you will be able to go ahead of others. But otherwise, till that time, you will raise points and then wait for some regulation to come.
You mentioned about coronal heating on the moon. Is this
not on the moon? No, this was actually it so happened that what instrument we carried on Chandrayaan-2 was looking at sun, and it had such a high sensitivity, it was able to give information on the coronal heating on the sun. Yeah.
okay? And different from direct radiation of the sun.
Yeah. Yeah, just behind you.
Thanks for the great talk. So, my question is, like this large temperature variation on lunar surface day and night. So are there efforts like how long-term performance of these can be achieved?
Yeah, see, currently, for example, if you see whatever Chase showed, within 100 mm depth, almost 80-degree gradient difference is there. So one of the things that people are talking about is using that material itself as a protection for suppose you build a habitat, use that as a surface so that the amount of heat conserved inside the habitat can be, actually this can act as a good insulator. So that is purely in terms of ensuring how much heat exchange is protected. But apart from that, you also need to worry about how to generate the required energy during the period of non-sunlit period. And that is where nuclear powered or radiation powered packages. Today work is also in progress between ISRO and BARC, where some effort has been initiated. In fact, we did carry a 1-watt RTG heater in the Chandrayaan-3 lander, but of course it was only just for the sake of nominal verification. But to do any serious task, you need to come up with power sources which can sustain, and those power sources which can be used for supporting the activities of the other things.
Thanks.
Questions?
Yeah. Yeah. Of course, if you look at the challenging phase, it is, see, I joined ISRO in 1975, and I joined for a program at that time called Satellite for Earth Observation. It was the first satellite which was building an imaging instrument on a spinning platform. So we were building a camera which could take pictures of Earth on a spinning platform. So our problem started with building instruments for that. And then the very first mission, it was not a success. The first attempt to turn on the camera resulted in a lot of corona and disturbing the entire satellite. So we went through a phase of learning from the failure, and then after 1 year of intense simulation, we were able to identify how we can turn on the camera after 1 year. So in Bhaskara 1, we went through such a phase. So, but basically what I wanted to try to tell you is, the journey from 75 till recently also has been one of newer and newer challenges all the time, trying to do something beyond what you are capable of today. So in that process, two things become very important. One is, unless you push yourself, you cannot go beyond your current level of performance. And when you are trying to push beyond what your current level of capability, you are bound to be actually bestowed with failure, and you need to understand how to deal with those failures and make sure that use them as your stepping stone for success. If you see right from the first activity where Bhaskara won our television camera payload, it was a very complex system involving high voltage system and then mechanical activities, etc., etc. From that, the very first failure showed us that it is very important to get into the aspect of simulation, understanding, analysis, and then repeating the thing and coming up with testing methodology. So again, in Chandrayaan-1, we were originally planning that the mission should last at least 2 years, but we failed within about 10 months. And then in Chandrayaan-2, we did not succeed in landing. So in all this, we see that challenges are going to be there, and you need to push yourself to achieve beyond your current level of capability. And failures are part of your routine, so you should learn to live with it. And if you are capable of dealing with that, then you can achieve success. Probably you can say my own journey in ISRO has also shown that this requirement of being able to look at what happens beyond your own ability and your knowledge is important. Yeah, please. Please go ahead, sir. No, you go ahead, sir. Nobody is there.
No, the other ISRO mission is the L1 mission,
Yeah.
which is being done to put this spacecraft at the Lagrangian point L1
Yeah.
to study the corona dynamics.
Yeah.
How is it going on now?
Yeah, currently in terms of the mission itself, if you see, it has achieved, it has already completed one full orbit and it's continuing. Now the VLC, that is the visible emission line coronagraph, recently has sent one paper, so one publication it is getting. So there are some issues, but even with that, the coronagraph is able to provide information. They are going through the process of validating some of the observation and trying to learn from how to interpret the data, what you are collecting. See, like I was saying, in each new attempt you are doing, in fact, this VLC is probably an attempt in building an instrument which nobody else has attempted so far, because they were trying to look at very close to the radius of the sun, 1.05. So close nobody had attempted to do. So obviously in doing that, certain difficulties are being encountered, and there are both a spectrometer there, and one of the spectrometer has already made some significant observation that is getting into a paper form. But apart from that, in terms of routine operations, all the other instruments on Aditya L1 is providing good results, and now VLC is going through a phase of validation in trying to retrieve some of the information that is being measured. Otherwise, this also is a very challenging mission in the sense that you are going to a point, an hypothetical point you are orbiting. So it is not a celestial body in that sense.
Thank you.
Sir,
Question.
Yeah.
thank you. Thank you very much for that very interesting talk on Chandrayaan mission, sir. I have a layman's question. You said ISRO is planning a manned lunar
Mission.
landing in 2040.
Yeah.
What are the possible technology demonstrations that could happen, which is different from the first manned moon landing in 1969?
Okay, so here one of the things we need to see is when the first landing on the moon happened, the purpose and the intentions were all very different. And today it's already technologically, if you see, a lot of differences are there, changes are there. But our need and desire to go to moon is primarily because as the country also keeps progressing in its own position in the Committee of Nations, you need to be competent and you need to be recognized to be competent. So space is a fourth frontier, and if space, you do not do sufficient activities, you will fall behind the others. So what are the things that you need to do? Obviously, you need to make sure that you can put man around Earth, and another closest celestial body is moon, and you should be able to land on moon and then use it for further activities. So what is going to be achieved by those missions, still a lot of things will happen between now and then. But right now, the basic objectives that are being attempted is build a technological capability of carrying humans from here, landing them on the surface of the moon, and then bring them back safely. First priority will be that. After that, you will look at some of the questions that you are looking at. Beyond that, what we will do. Otherwise, primarily, it's a demonstrating and building the technological capability of going from planet Earth to reach moon, land, and come back.
Thank you, sir.
Yeah, there is one here.
I just, so ISRO, as we understand, is also going through some structural changes in terms of what its purpose is. And one of the things that we keep hearing on is the role of academia, broader role of academia in the space program of India. Did you want to comment on that for
Yeah, I can definitely
benefit
say.
of Raman Research
So in terms of the changes, this is how things have happened, you can see. Initially, like I pointed out when Dr. Sarabhai started the space program, the whole objective was to provide capability. But now, by now, 75 years into independence, and see, you are the 5th largest economy. And also, if India wants to improve its economic capability, one of the key areas is space economy. Space economy is almost a $50 trillion economy. And if a country which has an end-to-end capability of building launch vehicles, satellites, and its applications, etc., if it has to take advantage of this space economy, it should make sure that there is more and more participation in the country, and it is not just one government organization which will work for that. That's how all the recent changes that have been done, where the government has made in space, that is a promoting and regulating agency. Then you have got an NSIL, New Space India Limited, for doing large number of the commercial activities like putting satellites into orbit, launch vehicles being built, and then enabling companies. Now all these basic mechanisms are through, and now that the government has also committed that we will have our own space station by 35 and our own landing on moon by 2040. Obviously, even the recent approvals of 29, 30,000 crores, if you look at, is not adequate. It's a component of the total. What is expected to happen is a huge amount of economic activity in space driven by private entities, and who will be not only taking care of all the activities needed for commercial Earth observation, then communication, navigation related usage, participating in that economy will all happen outside the government. Government is enabling them by bringing in appropriate the laws and then act supporting them. And in fact, very recently the NSIL and InSpace has come out with a process where a private constellation of consortium is going to provide Earth observation data by putting a constellation of satellites in orbit. Within next 2 years, they will have a constellation which will provide high resolution data, SAR data, hyperspectral data. It will all be a completely private entity. They will be doing this activity and providing data. So this is the one that is enabling. So in this context, if you see what is going to be done in the course of these next 2 decades, since there is a commitment by the government is definitely will continue to support. There is an opportunity for academia, researchers, and students to visualize what are the things that can be done, even without waiting for the government entities, whether it is Department of Space, to visualize what we can do independently, do detailed studies, do concept activities, and then push that as part of candidates. See, like I said, between now and 2040, there are going to be probably 10 to 12 missions to moon. Today, everything is not defined on that. So if there is an opportunity, if somebody, for example, RRI comes up with Pratyush-like thing, where they can say, if we do this, we are going to make path-breaking findings, etc. Such a thing can find an opportunity in then one of the missions, it will be accommodated and carried. So not only the moon, but also other celestial objects. The whole arena is open for, in fact, researchers to do. In fact, we are already seeing in Mysore, one of the college is actually conducting research on efficacy of the medicine in zero-G environment or microgravity environment. They have taken up the task all on their own. Now they have come to InSpace asking them, will you provide us an opportunity to put this payload in the space? So that is going to happen very shortly. So a lot of private institutions, academic institutions, as part of their research activity, can take up many of these things. And what we expect to see is a huge spurt, because life outside planet Earth brings in a huge opportunity in a very wide area of domains.
Yeah, thanks again. This is related to a lot of experiences gained by ISRO, the space agency, in terms of the space flight itself, flight mechanism, spacecrafts and so on. How much of it is fed back to the university education, and what is the mechanism exists in ISRO to feed this knowledge back into the education stream?
Okay, see today what's happening is, like just we were talking about, InSpace is trying to promote the space activities in India, and also they are conducting a lot of courses now for available both for public, anybody who is interested, even company people. They are getting into, like for mission studies, a lot of activities that are done are getting converted into small courses, and these courses are being conducted by ISRO experts on areas of special interest for space engineering. And today you're also seeing many academic IITs and ISRs are starting department space engineering, etc. And all people who have come out of ISRO are actually, their expertise is being funneled through InSpace into both private entities and academic institutions. So right now it's all in a, you can say, work in progress. Probably you will see the results coming out in next few years.
Any more questions? I have a question. So what kinds of technologies are directly in the roadmap leading towards 2040s?
Yeah, technology in the pipeline is like, our next important thing is sample recovery, and then docking in space, and then space station itself. Each one of them is a huge activity. Actually, in terms of technological elements, if you look at for that, there is a large amount of work that requires to be done. So the difference is today, because the government has already committed, just few months back also, a year back, we could not have told what we are telling you today. But this commitment is there in the country. Opportunity is there both for academia and institutions to pursue on their own without having to wait for. Earlier, what was really happening is any academic institution was all the time trying to look at what ISRO is doing, whether this can work. Now that is not necessary. Actually, this mindset also has to change. If you can come up with a very different idea of what can be done, you don't have to worry about what we are doing within ISRO. Then you can tell. Today, in fact, I'll tell you, one of the things that has happened is, there's a company in Bangalore, Bellatrix, which is creating such a, in a way, havoc, I can say. See, we were all used to being told that the low Earth orbit, you should not come below 400 kilometer, 300 kilometer. Why? Because when you come down to lower orbit, the amount of time you spend in that orbit is very small, and because the longevity is less, you have a problem. But as the propulsion and electric propulsion and other methods of propulsion things are changing, by putting a satellite at 200 kilometer orbit and sustaining it by using some small force which is compensating the friction of the atmosphere or any drag effect, that small component can continuously compensate it and keep it in that orbit. So you can imagine, if instead of 400 kilometers you are able to operate it at 200 kilometer, the whole lot of difference that will come in terms of resolution and in terms of radar systems, the amount of power that you need, your reduction by a factor of 2 to 3, almost 10 times you will require less power for transmission, etc. So there is a huge change that can happen. It's again here where we need to see, it's only when you start challenging the current taken as granted. This is where experience makes a problem. If you come to me and ask, I will say, don't go to 400, 200 kilometers. But then you will think, why should I not do? What is the problem? How can I overcome the problem? If you find a solution, tomorrow that will become the norm. That is what, again, experience, what I was telling, was as an example. Today, already, Bellatrix has announced Project 200. It's already creating a lot of ripples globally, because everybody was used to thinking that lower Earth orbit are problematic. Now there will be more people who will come up with more innovative solutions. How to keep these satellites operating for longer durations there, and as a result of that, make a huge change. So what my suggestion is let your thoughts go wild and then try to make it happen. Yeah. Huh? Probably. SETI. Okay. Yeah.
Vinod, can you repeat with the mic? I think it's passed on.
Yeah.
Sir, any thoughts on SETI and interstellar mission?
Okay. Now, obviously, within ISRO itself, if you look at, we are not thinking of anything on that. But then, whatever related to that has to be done outside only. And
Thank you.
Any more questions?
you can ask
Yeah,
online.
Sanjita. Yeah, we can also check online. I can pass on.
What are the main scientific objectives for the Chandrayaan-4 mission?
Sample return mission is pick something of use for scientists. Now, some scientists will have to tell us where we should land, where we should pick up. See, technology-wise, it's a sample return mission. So we need to find appropriate, useful sample. And what is that appropriate and what is that useful has to come from scientific community.
Thank you. Yeah.
Biotech. So, any comments on that?
Yeah, here again, basically what we are trying to promote is more and more academic institutions trying to find both funding for the research they want to do across departments in the country. So biotechnology also, if you see, there's a huge interest in surviving, keeping life intact in space, and both in terms of monitoring and providing appropriate environment, appropriate food. So there's a huge amount of activity that is involved in that. So it is, many ways you can say it is like groping in the dark. So we know that we have to do some things. There are other departments who have done some activities. So bring them together and then try to make sure by the time the actual missions get defined properly, these things would have reached a stage where you are able to conduct appropriate experiments. So we want more and more participation by people in these ideas.
So one question. This is related to who charts the Indian space program plan for the next 20 years and who monitors it is sustained and improved?
Yeah, of course, Department of Space is actually the responsibility in the sense is how to make use of space technology for country's benefit. That is the prime objective. If you keep everything that it is doing is being monitored through that system. Initially, the requirement was how to solve your communication problem, navigation problem, cyclone, monitoring, weather, like that you went on up to a certain point. And then today it's also in terms of strategic requirement of how to protect yourself. And then by the time space has become a contesting area for international power, so then you also have to make sure that you have the corresponding thing. So in all these things, these are diversifying. Now they are getting delineated. So whatever is in terms of enabling the technology for development, Department of Space will take care. There is a Defense Space Agency which will make sure that how to make use of the space for protecting and then protecting the assets that are there. That will be the Defense Space Agency. So like that, things will start getting separated and delineated as the demand keeps growing.
Any more questions? All right, if not, let's thank Shri Kumar for a great talk. And I'd like to invite our director to present a memento.
Thank you so much for such an inspiring talk and also guiding us towards what we could do to work together with the space program and So this again pointed to the capability of RRI's amazing workshops. Here's a in-house memento. expect to give this to every
Okay.
speaker, the Founders Day.
Thank you. Thank you very much.
So much.